sunscreen, and it is white to prevent absorption. But you coat it with a dye, and the dye absorbs the light. The dye then injects an electron into the energy levels in the conduction band of the solid because it sees the asymmetry. That leaves behind a vacancy where the dye was. It doesn't have the electron anymore. And then that vacancy is filled by something in the solution, in the gel, like a battery. This is like a solar battery that runs itself in sunlight. Now, this system was known for 50 years. And the problem was that only a monolayer of dye was efficient at absorbing light and injecting electrons. You could absorb more light with multi-layers of dye, but the layers, because the mobilities were very low in organic materials that would absorb the light, wouldn't effectively transfer their excited states to this electrode. They'd never make it. They would just recombine. So you needed a lot of layers to get a lot of absorption, but when you got a lot of absorption, you never got a lot of current. When you used a monolayer, you got a good yield of absorbed photons, but you didn't absorb many photons. What's the solution to that? Make a porous network to get a lot of absorption, but only keep a monolayer of dye at any one time. This is the fundamental property of what was discovered in 1991 by Brian O'Regan and Michael Gretzel. He's, I think, the third most cited author in the world of science because of this. And it has spawned a cottage industry among scientists to work in dye-sensitized solar cells that have the same asymmetry that we talked about from these two solid junctions, but one of them is a liquid. And the beauty is that you don't need expensive processing. You can make this, in fact, with paint, because TiO2 is the pigment in white paint, and the dye can be the dye in blackberry juice. If you look on our website or others, you can see how you can get electrical juice from juice. There's a high school experiment called Juice from Juice. And so people are now trying to optimize the surface area, trying to optimize the dye, because there's a lot of dye chemistry from photography heritage of red dyes and blue dyes, and ones with the right energies to inject electrons into TiO2, and ones without the right energy. And you can make solar cells that have all these different colors and different band gaps. And there are, I think, now 10,000 papers literally on dye-sensitized solar cells. And there are actual modules that you can buy. Their efficiencies are 7%, but they're competing with an existing product, solid-state solar cells, that have higher efficiency and comparable cost. So the nice bad thing about solar